Okay. Good morning, everybody, and welcome. It feels a little drafty in here. We just shut these doors. Maybe the radiators will start warming it up a little bit. But glad to see you. I think I saw +3 on my thermometer this morning, so it's, I guess, and they said there was flurries in Barrie or something like that. So, when it hits Barrie, it can't be far away from us. So good morning and welcome. And yeah, Halloween's tomorrow. There's little Baby Yoda. I just put in an announcement this morning. So actually, some people mentioned on the pre-class survey this morning that there was a typo in the PDF part of problem set 6, which is due after reading week. There's just a missing spring constant, which you absolutely need to solve that problem. 10. So there's an announcement up there. Thank you for that. I always like getting told when something bad's happening. Let's just go over quickly what's going on the next 2 or 3 weeks. This week, today I'm finishing off chapter 7 on energy, and that's what the practicals are about. So practical that you're doing this week is these little poppers. You push them down, and then they spring up. So Jonathan set that up here for you, but I put a little video. I usually do the experimentalist video where I try to do it myself, and then the theory video. But basically, you've got a spring with a spring constant, which you can measure somehow, and then it stores 1/2 kx squared while the thing is sitting there, and then that gets converted into, initially, it's kinetic energy when it leaves the spring, and then it goes up to mgh, the gravitational potential energy. So you're trying to compare the energy at the top of its little flight to the spring energy. So good luck with that. It's kind of a fun experiment, the flying pylons. Then we got reading week next week. So next week there's no classes, no practicals, I'm also not holding office hours. So it's a break for everybody. Hopefully it's time to kind of catch up on your sleep or catch up on what you've got going on Crave or whatever. So, okay. And then the week after reading week, we come back, finishing off chapter 8, continuing on with rotation and torque kind of stuff. We've got a mock quiz happening because there's a term test on Tuesday, November 21st. So not the week you come back, but the week after we come back. And that's a Tuesday evening at 6 p.m. And that'll be on chapters 5, 6, 7, and 8. So four chapters in one. How are we doing with that? Just raise your hand if you want me to throw you the mic ball. Okay. That's what's going on. Somebody asked, are we expected to memorize the equation for the gravitational potential of Earth and any object? Well, I think it's a good equation, so I would write it on my aid sheet if I were you. That's what the aid sheet's for, so you don't have to memorize any equations. Don't understand how the change in momentum can be negative. So yeah, my answer to that really is just it's final minus initial. So this is from problem set 5 this week, question 17. What you've got is, I would say, delta P is equal to P final minus P initial. So it's going to be the mass times, I would say, kind of something negative, I don't know what it looks like. Maybe 55. That's going to be 0. So that's 50 centimeters. So it's probably 0.55 meters per second, right? Because you have to convert from centimeters to meters. This is just taken off the display from your actual graph from last week. And then you minus the initial, which was minus plus whatever it is, plus 0.6 meters or something like that. So it's minus a plus, you get a negative. It's trying to make sense. You've got something going positive. It ends up going negative, so you've got to give it that push in the negative direction. When doing impulse, momentum, and work energy questions, we should always take into account the values are negative and positive because they're vector quantities. So this is a bit of a mixed up question, so I want to straighten this out. So vectors have direction. And impulse and momentum are vectors. So when you set up your XY axes, the components, if they're positive or negative, are indicating direction. And I think when we do 1D motion or something like you did last week actually, the x-axis, so plus is one way and minus is the other. But that's not true for work and energy. Work and energy are not vector quantities. There is sometimes a sign, well not always, like kinetic energy is always just positive. Work has a sign, and the sign there is used to indicate if we're kind of adding energy to something or if we're taking it away, depending if we're speeding it up or slowing it down, I guess. Oops. The sheep are anxious to come out. So we got that one. So the first part is correct of this question, and then the second part I don't like. So energy and work are not vector quantities, is what I'm trying to say. These are vectors. Vectors. And these energy and work are scalars. Okay. You don't have to take direction into account for a scalar. Okay. Hope that's helpful. And this was Daisy's birthday today. Happy birthday, if you're here. Some jokes. Found out that Albert Einstein was a real person. I thought he was only a theoretical physicist. Yeah. Okay. Okay, why are sports cars subject to more regulation than regular cars? With great power comes great response. This is a very good mixing of both physics and Spider-Man in one joke. Okay, so that's, and it also segues into what we're doing today. Power is how fast work is done. It's work done divided by the time interval delta t. And it's got its own unit of power, the watt, named after James Watt, the developer of the steam engine. A joules per second is a watt. So like a 100-watt light bulb uses up 100 joules of energy every second. So, and a kilowatt just means 1,000 watts. So, okay, let's do a top hat question. Get things going here. Rita raises a 10-kilogram package at a constant speed to a height of 2.5 meters in 2 seconds. If she were to raise the same package to the same height, but in half the time, what would change about the work done and the power? Snuck up on me. Survey says... that the work would stay the same, but the power would double. Ooh, what did I do there? Oops. There we go. It worked. So I think that the work done is just the change in the potential energy, mg times 2.5. So this would be the same for both because it's the same package and it's the same height. And then if delta t goes down, then the power goes up. Because power is work divided by delta t. So I like B. Good on that. There was a pre-class quiz thing on this morning. Person B does twice the work of person A and in 1/2 the time. So that's again, same thing, divided by delta t. So that's P1, something like that. You've got P2 is going to be 2 times the work divided by delta t divided by 2, 1. It's going to be 4 times P1, something like that. 4 times the power output. Okay. So sometimes where you hear the word kilowatt is in, if you look at your power bill, it comes in kilowatt hours. So it's sometimes abbreviated kWh on a hydro bill. And what that means is it's the amount of energy used by, if you're doing 1 kilowatt over an hour. So what do you pay for when you buy electricity? You pay for energy. Energy is in joules, I guess, but joule turns out to be a very small amount of energy. So like if you run your dryer, that's about 1 kilowatt. And if your dryer takes an hour to run, a kilowatt hour is 3.6 million joules of energy. And it turns out that that's what they charge you for. It's about 15 cents. There's energy sources. I pulled this recently off the Ontario website, just showing sort of where does the energy come from when you turn on or you plug something into your electrical grid here in Toronto. It's 34% nuclear, 27% coming from some sort of, well, it's gas here, gas or oil. So definitely carbon stuff. Hydro just means the dams, like Niagara Falls. There's various dams around where there's some sort of nearby waterfall, but some of that water is turning turbines and generating electricity. It's about 23% of our energy. There's also a lot of wind farms around generating 13%. Solar panels, solar farms, or residential solar is right now at 1%. And other kinds of biofuel, less than 1%. So that's where energy is coming from in this province. Already did this. That slide out twice. There you go. The price of electricity purchased from Hydro One is about 15 cents per kilowatt hour. So let's say that your clothes dryer uses 5,000 watts, for example. And I would just write here the rate. The rate is 0.151. I would call that dollars per kilowatt hour. So you've got money on the top of the unit and then energy on the bottom of the unit. But it's not an SI unit, it's using this kWh as a unit of energy. Or 1 kWh equals 3.6 million joules. Okay. And then you could say your cost is equal to your rate times your energy that you use. And that's going to be equal to the rate times the power times your delta T. Okay, so it's 0.151 dollars per kWh, and then multiplied by 5 kilowatts, because that's 5,000 watts, and then you can multiply it times 1 hour or something. And then I think the way the units kind of work is your kilowatt cancels kilowatt, and your H cancels H, and you just get dollars. I didn't do this before, but we can pull up my calculator. 0.151 times 5. It's only about 75 cents, so $0.755. It costs about 75 cents of electricity to run your dryer for an hour. Okay. How are we doing on that? We'll do another top hat. Sports car with great power accelerates from 0 to 30 miles an hour in 1.5 seconds. So how long would it take to accelerate from 0 to 60 miles an hour, assuming the power of the engine is independent of velocity and neglecting air resistance? So, what I want to do, independent of velocity, what I mean here is that assume the power is constant. If you double the final speed, how will that change the delta T, do you think? So these guys are saying they think it's something to do with energy, maybe even kinetic energy is my hint for you. Power is change in energy divided by change in time. Right? Okay, 30 seconds. Pressure's on. Okay. Let's see what people are saying, and then I'll walk you through my reasoning. Yeah, this is one of these Monday morning. Okay. So I think both 3 and 6 were good guesses. I like 6, and I'll show you why. The work done on the car is equal to the change in energy of the car. And so it's P is equal to W divided by delta T is constant, right? That's what we were trying to assume, I guess. So you can rearrange that to delta T is equal to W over P. And I think the work done is going to be 1/2 mv final squared. That's sort of where I'm getting at. Because it's the kinetic energy it starts with 0 kinetic energy, ends up with a bunch of kinetic energy. That's what your engine, I guess, is doing in terms of energy, is it's adding to kinetic energy of your car, which makes you go. I think you use up fuel and you convert it into kinetic energy. EF is doubled, so that's why I got D. VF squared goes up by a factor of times 4. Whoop. So delta T2 is equal to 4 times delta T1. And 4 times 1.5 seconds equals 6. That was my reasoning. Questions on that? You guys are quiet mood, yes. I'm going to toss this to you. Whoop.
How do we determine between power and momentum when we're writing? Are they both P's?
Oh, that's a really good question.
No?
I think I just use capital P for power and I guess lowercase p for momentum. We're sort of running out of letters in the English and Greek. So we start reusing, it's the letter recycling program, so I apologize for that. It is confusing, right, too, because I was thinking about this, when you talk about momentum, the momentum is coming from like the static friction on the bottom of the wheels, it's giving some momentum to the car, but when you think about energy, I tend to think about the fuel being used up in the engine and being converted to the kinetic energy of the car, and so. Okay. All right, so I think we're going to move on now to this gravity review. So, the idea here in chapter 7, we had an equation for gravity in the universe. Do you remember all this? The force of gravity between any two objects, m1 and m2, is gm1, m2, divided by r squared, where r is the distance between their centers. And somehow we reconciled that capital G was this crazy number, 6.67 times 10 to the minus 11. And then if you are near the surface of a planet, which has mass of 10 to the 24 kilograms and a radius of 6,000 kilometers, then the G times m1, where m1 is the mass of the Earth, divided by r squared, where r is the radius of the Earth, gives you lowercase g. It turns out to be 9.8. And then you multiply it times m2, which is the mass of the little object that's sitting on the Earth. So that's the force. Well, it turns out that there's a gravitational potential energy associated with any two masses as well. And it looks like exactly the same equation, except now it's r on the bottom, not r squared. But basic idea is that if you take two masses, and this tennis ball and this pylon, if you separate them apart from each other, you're doing positive work, so you're adding gravitational potential energy. So the radius is getting bigger, so this is getting less negative. So they have I think there's a limit, right? The limit of 1 over r as r approaches infinity is equal to 0. So two objects would have 0 gravitational potential energy if they're infinitely far apart. And you get to 0 by starting off with some negative potential energy. So we have chosen the 0 point of this potential energy to be at r equals infinity, where the masses have no tendency or potential to move together. And then this gives the potential energy of masses m1 and m2 when their centers are separated by a distance r. And there was this question, 2 lead balls each have a mass of 1 kilogram. Their centers are located at 10 centimeters apart from each other. So m1 equals 1 kg, m2 is equal to 1 kg, r is equal to 0.1 meters. So you convert everything to SI units, and then you say that U sub g is equal to negative capital G m1 m2 divided by r. And you get negative 6.67 times 10 to the minus 11 times 1 divided by 0.1. And I get, it's negative 7 times 10 to the minus 11 divided by 0.1 equals negative 7 times 10 to the minus 10. And that's going to be joules. Makes sense? And that's U sub G. Okay, so you got that? And that's how you plug in. It's always, always, always a negative number by definition. Okay. So the gravitational potential energy is 0 when objects are infinite distance apart. The only way to add, you add positive energy to a system by doing work. If these two objects are attracted to one another and I want to separate them by pushing them away from each other, then I must be doing positive work on the pylon and positive work on the tennis ball. So how can you add energy to a system and then get it to be 0 when they're infinitely far apart? It has to be negative energy. That's why we define it to be negative. So gravitational potential energy is negative when objects are closer together, and more negative the closer they are. And it kind of looks like this sometimes. If two things are close to each other, they have some big negative, you do work to separate them out to infinity, and the final energy is 0. For an object that's on the Earth, we can set m2 equals m, the mass of the object, and m1 equals me, the mass of the Earth, and r equals re, the radius of the Earth. But you're not going to get mgy, right? Or are you? I think we're going to try to derive that, but first let's do a top hat question. See if you getting the idea. Let's do this one. Let's just say we've got 2 planets, 1 and 2. Configuration A, the 2 planets are, or configuration B, the 2 planets are further apart than in configuration A. So if you consider the planets as a system, which one has more gravitational potential energy? Or I think you might see on top hat a choice C, which is that they have the same gravitational potential energy. Think about that, discuss, pick an answer. Yeah, so what do I mean by more? More meaning less negative, I think. Is that right? Okay. You have to add energy to get something up to 0 if it starts off negative. Is it better to have less debt or more debt? Less debt is better, right? So this is a negative number. Good. 20 seconds. Okay. Survey says configuration B, they're farther apart. I had to push them to be farther apart. I had to add energy. Another way of looking at that, if you look at this equation, is that, so B is the answer I like. R is bigger. R is on the denominator, but the whole thing is negative. So it's less negative. So like closer to 0, where 0 is the highest thing. Okay, so we need to actually reconcile something, which is this. Let me see if I can do it. There's a bit of math here. So let's work through this. Okay. What I'm going to do is, remember I kind of said, where was it here? That this is the gravitational potential energy of something sitting on the Earth's surface. Well, what if you move it? So if I move it to some distance y above the Earth's surface, then what is that going to look like? So I'm trying to get mgy. So what I can do is multiply the top and bottom by 1 over r sub e, the radius of the Earth. So times, I'm going to do a couple of mathematical tricks and try to get at something. So this is going to be negative g times the mass of the Earth times m, the mass of the object, divided by the radius of the Earth, and then divided by two fractions, re divided by re plus y divided by re. And so you can write that out as u sub g is negative g m e m divided by re times 1 over 1, because re over re is 1, plus y divided by re. So the idea is that if I move this object, so here it is at re, if I move it up a distance y is much less than the radius of the Earth. So y divided by re is a very small number. And so what I tend to do in math is I set that number to be epsilon, which is small. So we're going to do an epsilon proof here. Epsilon equals y divided by re. Okay, and so the idea here is that epsilon is much, much less than 1. And also I'm going to set that g, lowercase g, is equal to capital G times mass of the Earth divided by re squared. We actually did that before, the 9.8 meters per second squared. So gme over re is equal to lowercase g times re. So we can rewrite this equation now. U sub g is equal to negative lowercase g times re times the mass times 1 over 1 plus epsilon. And now I'm going to do a trick where I'm going to multiply top and bottom by 1 minus epsilon. And I'll show you why. So the top is going to be 1 times 1 minus epsilon, so it's 1 minus epsilon. And the bottom, whenever you have a plus b times a minus b, you get a squared minus b squared. So 1 plus epsilon times 1 minus epsilon is just 1 minus epsilon squared. And the reason I did all this is because this reasoning. Since epsilon is much, much less than 1, then epsilon squared is very small. You can neglect it. That's what we tend to do with these epsilons, is we try to get something in terms of an epsilon squared, and we just cross it out. Because if epsilon's small, epsilon squared is that much smaller, so we can neglect it. So now we do that u sub g is approximately equal to negative g times re times m times 1 minus epsilon. Okay, since 1 minus epsilon squared is approximately equal to 1. Does that make sense? That's where the trick is. And then it all works out. So you get u sub g is approximately equal to negative g times r sub e times m plus g times r sub e times m times y divided by r sub e, because I've plugged back in our equation for epsilon. And so it's equal to, what we'll do is we'll set this equal to u sub 0, and we get u sub g is approximately equal to u sub 0, whatever that is, plus g, these re's cancel, by the way, times m times y, mgy. So there's a arbitrary 0 point in MGY. Remember I said, oh, I could set 0 to be right here on the floor, or I could even set 0 energy to be up here on the table. That's arbitrary. So that's that U sub 0 part. And then MGY is what we know from before. So these are the same equation. They just look really different. And notice how it become positive as well. As y goes up, you get to a positive number. So that's good. It's good too. Okay. We've done a tricky top hat. We've done an epsilon proof. Anything else? That's for Monday morning, yes, sir.
Yeah, I just wanted to ask, like, what do we use like epsilon for? Because what's the use of it?
Well, I didn't want to write all the little y over RE a lot of times.
Is it just like a placeholder for a value super close to 0?
Yeah, it just sort of reminds me when I'm doing one of these approximations. So this is an approximation. And so at some point what I want to do is see like there's an epsilon squared, like something like 1 plus or minus epsilon squared, then I can just cross that out. So it's a handy little trick. But yeah, it's a placeholder. It's a really good point. Yep. Mike? Yes.
Thank you. I want to ask that where is the extra U0 comes from? Is that because of like the difference in reference frames or something?
Yeah, exactly. Well, kind of like reference frame, it's wherever you define the 0 potential energy to be. So I think there was Amber and Bill, they had a rock, and they defined 0 energy be at different places. So that's where this U sub 0 comes in. So if we define 0 energy to be when y equals infinity or something like that, which is, I guess, where it would be, then you'd have to add this other U sub 0 or something. So, but what we do is we just set it up so that U sub 0 is 0. We define U sub, gravitational potential energy to be 0. So the equations aren't quite exactly the same because they have a different 0 point. Okay, really good point. Anybody else? Okay. It's hard to keep an eye on you guys because you're all spread out. I feel like there's enough room, like enough empty seats that we could all. Anyway, it's okay. Everybody's good. Where they are, it's all good. Okay. Let's see here. What do I have? Oh yeah, well, maybe we can try to prove it. A cat starts at ground level and goes up to the restaurant of the CN Tower. Okay, so how are we going to do that? Well, we could use the approximate equation that U sub g equals mgy and calculate change in gravitational potential energy of the cat. And remember, it's always the delta U that matters physically, the change, not the absolute value. So we could say delta is mg, which doesn't change, y2 minus y1. So it's going to be 350 meters minus 0. Then you get 17,000 joules. So that's okay. But next, let's try, so that was actually an approximate equation, which assumes that g is constant. So we could try to do the same thing for the cat using U sub g equals negative gm of the Earth times mass of the cat divided by r, and see if we get the same answer. It's hard. So what you do is you say that the base of the CN Tower is at some distance from the center of the Earth, and the top of the CN Tower is farther. So I think there's something seriously wrong with my significant digits here. I doubt that it's really... But anyway, the difference here looks like that. It was a bit hard to do in my calculator, but I did get 17,000, so it makes me feel like I kind of did something right. Fun with calculators. And so again, remember, it was like Amber and Bill with the rock. What matters is delta U, the change in potential energy. And it doesn't matter which equation you use. This equation is technically better because it's the true one, whereas mgy is an approximation. But you get the same answer for CN Tower-sized objects. Okay, guys. All right. What else do we have? I think we got escape velocity. We should talk about that. We're getting towards the end of chapter 7 here. So the 0 points of the two equations are quite different. mgy assumes 0 is at the surface of the Earth, I guess, whereas negative gmm over r assumes that 0 is infinity. But since the 0 point's arbitrary, the two equations are physically the same, as long as you're not too far from the Earth's surface, which we usually aren't. Okay, this is a railgun, the idea that you could use some sort of electromagnetic force, like you're going to be taught about in Physics 132, to launch something at some initial speed. But basically, if something goes at some initial speed, what's the minimum speed that you could completely escape Earth's gravity? Well, you can use this equation. I'll show you how it works. Sorry there. In order to get to r approaches infinity and stop, the final energy must be 0. So you go out to infinity and park it there. So at the end, your gravitational potential energy is 0, and also your kinetic energy is 0. So you want your initial energy to be at least 0. And you work that out to say that you can write it out, initial. You got some rocket or something, minimum speed of a spacecraft at some v initial on Earth's surface. And then final, it's a little, let's call it deep space. Maybe there's a restaurant at r equals infinity. You can't eat. It's way far. Okay. Where's infinity? Like way far. Just keep going. But v final is equal to 0. And what you do here, by the way, is you neglect air resistance. That's kind of important. It's not very good, but you can do that. So the simplifying diagram step, if you want to put it, looks something like this. K initial plus UG initial, I guess plus the work or something, is equal to K final plus UG final. So if you write it in terms of equations, 1/2 mv initial squared minus gm of the Earth times the mass of the object divided by r plus 0 equals 0 plus 0. So you just end up with, you can actually, there's m's on both sides of this equation. So it doesn't matter what the mass of the rocket is, because the m's luckily cancel. So that's interesting. And that was on your, pre-class quiz. Go back to blue. You got v initial squared over 2 equals g mass of the Earth divided by radius of the Earth. Sorry, this should say RE. Right? So v initial equals the square root of 2 times g times mass of the Earth divided by radius of the Earth. You can plug in numbers for all that stuff. You got 2 times 6.67 times 10 to the minus 11, I guess, times 5.94, I think, times 10 to the 24 kilograms divided by 6.4 times 10 to the 6 meters. And then take the square root of all that stuff. I got 11.1 times 10 to the 3 meters per second. So that's V initial is 11 kilometers per second. This is the escape speed of Earth. It only depends on the mass of the Earth and the radius of the Earth. It does not depend on the mass of the object. So it'll be the same for a rock as it will be for a big spaceship. It's the escape speed. And every surface of every planet has its own escape speed. I think you were asked on the problem set to find the escape speed of Mars or something. It's different. But 11 is what it is here. So, idea being that if you could launch something at 11 kilometers per second, anything, it would go forever. Problem is air resistance. Anything going this fast in air would immediately explode. But the point is that it doesn't depend on us. Okay. If you can get outside the Earth's atmosphere, you need to get to this speed so that you never come back down. How do the escape speeds for two rockets, first with a mass of 2 kilograms and the second with a mass of 20 kilograms, compare? The escape speed for the rocket with the lesser mass is the same as that for the greater mass. It doesn't depend on mass. There's also something about this equation which is interesting, is that you can change the mass of a planet or change the mass of the radius of a planet to make this escape speed any speed you want. So if you were a theoretical physicist like Einstein or something, you might change it around till you get the speed of light. Because in special relativity, nothing can go faster than the speed of light. That's an important constraint in physics. So if the object's escape speed, like a planet's escape speed, was faster than the speed of light, then nothing, not even light, could leave that surface and escape out to infinity. So we call that a black hole. Star would be completely dark, or the planet would be completely dark. Okay. You guys are restless. You know what? Thank you so much for sticking through on a Monday morning. We're going into Torque on Wednesday, so have a look at that. And here's a place you should not put your door handle, right in the middle of the door. It might look aesthetically pleasing, but why not is the question. There's a physics reason for that. So maybe think about that between now and Wednesday. I'll see you then.